All right, welcome back to JICHE, where we talk about current results from the Kitchen Research Group. Today I'm going to talk about some work that Jenny Zan and I finished and published recently on the origin of Stokes-Einstein deviation in liquid aluminum silicon, and the DOI is down here. You'll find it in the video description. Okay, so what is the problem that we worked on here? In liquids, the diffusivity and viscosity are often related to each other in a simple way that's shown down here. That is, here is the viscosity, here's the diffusivity and the temperature. And for many liquids over a really big temperature range, this is a constant. And so if diffusion goes up, viscosity goes down, and so forth, and the whole thing is a constant. So what that is important for is that in liquid metals, they're usually at a high molten temperature, and it's difficult to measure both of them. So if you know one, you can use this relationship to calculate the other if you're doing a design, for example. Now, as you approach the melting point, this relationship often breaks down, and D is no longer a constant. And that's what we wanted to look at in this work, is what happens in silicon aluminum, which is used for a lot of metal parts or casting parts. And how do we find out what's going on at the atomistic level? And we use molecular dynamics for that so that we could simulate lots of silicon and aluminum atoms moving around. And we use the potential down here in this work. So what exactly does this look like? Here are two of the results where we show this region here that we have a constant D for at one temperature, and here we have another one at a different temperature. Or different composition. And so what you see is this kind of constant region over here, and there are error bars on here because in molecular dynamics there's lots of fluctuations, and so the dot indicates where the average is. And then where the vertical line is about the melting point for these compositions, and this is where we see the approximate deviation from up here. So what we found is that the viscosity changes faster than diffusion in this region here, and that's why this effective diameter is changing. And so the next question is, why is the viscosity changing faster than the diffusion? So when we go and look in detail at the diffusion coefficient, and I'll leave all the details to the paper and how we go about calculating these things, but what we find is over this whole temperature range that we looked, there's one line that fits this Arrhenius behavior for both compositions, and there's one activated process associated with diffusion. However, the viscosity shows two regions, and it's a little bit tricky. These slopes are not hugely different, but fitting two lines in here is better than any other model we looked at in terms of these residuals up here. And so what it looks like is well above the melting point, you have one activation energy, and below it you have a different activation energy. So something's happening with the viscosity, and this change in slope in the Arrhenius behavior is probably the origin of that Stokes-Einstein deviation. So what is affecting the viscosity is the formation of clusters. So as you approach the melting point, or as it begins to freeze, you have to transition from a liquid to a solid, and you go through a transition where you start forming clusters that last longer and longer. And so this graph shows you as you get cooler, you start getting more and more clusters that last more than a picosecond, and now you can start to think of this liquid as being kind of slushy. And it's well known that when you add clusters to a liquid, as the volume fraction goes up, the viscosity goes up. And so on the right-hand side, you can see the first thing that I showed you, where when we have the clusters there, we see the deviation like this. If we take the clusters out, which we can do in the simulation, we just don't count them, and only look at the liquid part, you see that in the liquid, the effective diameter is a constant. And only when we count the contribution from clusters do we see the deviation. So clusters are almost certainly responsible for the Stokes-Einstein deviation that we see, and they have a bigger effect on the viscosity than they do on the diffusion. All right, so that is the basis foundation of the talk and the main results. Near the melting point, we start getting clusters that form that live long enough to impact viscosity more than diffusivity. Those clusters likely lead to the deviation in the Stokes-Einstein deviation that we observed, and molecular dynamics was really good, a really good tool for investigating this. And there's a lot of details in how to do the liquids and how to calculate those properties. And so I invite you to read the paper and find out. So thanks for listening, and we'll see you next time.